to avoid any kind of interactions between the emissions from the two dots. So first I wanted to increase the interdot distance, and that I achieved by stacking two AAOs on top of each other and blocking most of the pores, because the pores on the AAO were very, very dense. And the other thing I wanted to do is try the degree of freedom to pattern the dots in desired shapes and sizes, and that I achieved by doing the E-beam lithography and draw a mask of desired shapes and then try to create dots in those shapes. So first I'll talk about the point number 1, that is increasing the interdot distance. So just to increase the interdot distance, I applied a very simple technique. Earlier I was using this method, number 1, which was only one single AAO plate stacked on top of MOS2 SiO2 Si, and then as I showed you earlier, I could end up with MOS2 dots, very well spaced and with controlled sizes. Later, what I did was stack two AAO templates randomly on top of each other, and this was done in order to block most of the pores, because this was very dense template. So most of the pores were expected to be blocked, and after that, only few pores were open, and the interpore distance could be increased. And then I would end up with MOS2 dots far away from each other. So these were this would act as better single photon emitters rather than very closely spaced MOS2 quantum dots. Here is representative SEM images. So this area is 2 stacked sheets. This area is 1 stacked sheet. And just for better understanding and better imaging, I used flakes, monolayer flakes instead of film, so that I could just easily see the difference between the MOS2 layers and the bare surfaces. This is a zoom in image of the same. And then here you can see that after the AAO was peeled off, the interdot distance here, where only one sheet was stacked, is the same as expected. It is very dense, but the interdot distance in the area where 2 sheets were stacked is very, very far away from each other. To summarize this result, here, as we can see, I have put images in 2 different resolutions. This is one AAO stacked sheet, which have very beautiful, nice MOS2 dots spaced, like equally spaced from each other, but they are dense. And in the second method, where I tried to gain some control over the patterning, I could actually indeed separate the dots from each other, like here and here. This is also another representative SEM images. Here, this is after reactive ion etching. So the rest of the MOS2 everywhere is gone, and only gold dots covered underlying the MOS2 is remaining. And then finally, after the wet etching of AU, all I was left with is MOS2 dots on the top of the silicon wafer. So these would in future act as a single photon source, which were very, very far spaced from each other. So we expect better transmission, better emission from these. I would now start to discuss about the second point that I tried to do is patterning these dots in desired shapes and sizes. And this was achieved by doing the E-beam lithography. So what we did is we used our basic template of MOS2 SiO2 Si covered with AAO, and then we put E-beam resist. And as a E-beam resist, I used suspended PMMA film. Because PMMA couldn't be directly coated on AAO, because the roughness of the AAO is very high, we dried up a PMMA film, the E-beam resist film, and deposited it directly on the top of this. After that, we used etching mask. And after using the etching mask, we covered it with gold again. And by following all the E-beam lithography processes, we could create gold dots with MOS2 on the top of silicon wafer. Later on, following the same method, when I did reactive ion etching, all I remained with is the very well patterned MOS2 quantum dots on the top of silicon wafer. Here is some representative OM images. These are only optical microscope images. Here we use suspended PMMA film on the on-chip MOS2 directly stabilized on the silicon wafer. And after the E-beam lithography, as you can see, well-spaced desired patterns. I chose UNIST because that is my affiliation for right now. And I could make very well-spaced quantum dots directly on the silicon wafer, which would indicate that in future, this fabrication technique would provide liberty to make quantum dots of whatever shapes and sizes and whatever interpore distances. So what I would like to use these MOS2 quantum dots in future is like I expect this kind of response from the well-spaced MOS2 dots, which is I would like to get very enhanced and single photon emission from these well-controlled quantum dots, like in this previously published data. And I would like to do near field spect. Actually, we are doing near field spectroscopy on these samples, and we are already getting good emission results, but we are trying to improve the data. And we are already in process of preparing the manuscript for this work. And so that's all. And I would like to conclude my talk by saying that we synthesized quantum dots of transition metal dichalcogenides with very well controlled sizes. And I believe that this technique can be easily extended to any novel 2D layered material coming up right now. So we can use any new quantum emitters, any new single photon emitters, which are layered material, 2D materials that can be stabilized on silicon. And then this technique, the fabrication technique is so basic and hassle-free, we can extend it to any of the novel 2D layered materials. And then the interdot distance also could be modulated with the quantum dot size. So we can choose the dot size, and also it can be patterned in desired shapes and sizes, which gives us liberty to make very good shapes and sizes in the existing on-chip silicon technology for further integration in quantum computing, etc. Of course, it is a very far-fetched plan. And then the near field optical spectroscopy of such quantum dots is desirable for single photon emission in future. And that's it for my current work. I would like to thank all of you for listening. Thank you very much.
Thank you, Dr. Swati. We are really glad to have you addressing all of us. Now, I would request Dr. Swati and Gopal sir to accept our token of appreciation from the team CIR. May I now request Dr. Amit Majumdar, Session Chair, to deliver the vote of thanks to all the speakers.
Thank you, Vaishali. It's my privilege to have been asked to propose a vote of thanks to the esteemed speakers. I, on behalf of Symposium Organization Committee, extend very hearty vote of thanks to the honorable speakers, Professor Rajendra Venugopal, Director CSIR NPL, and Dr. Sati Singh, to share their precious knowledge and valuable research work on the single photon emitters and detectors. Professor Venugopal, he is one of the authority in the field, shared all the details of the current quantum research on the emitters and detectors. Obviously, due to the time limit, he cannot explain fully, but he enlightened us with a lot of new things, what is happening in the advanced field. Dr. Sati Singh obviously presented very nicely, very precisely her presentation and his work actually, particularly the explain in details that how the fabrication in the TMTC quantum dots on the embedded silicon and silicon oxide wafer. Thanks Sati and Dr. Venugopal. And once again, I would like to thank both of them speaker, and also thank you all the listeners who have participated in the online seminar. Thank you all.
Thank you so much. Thank you everyone for such a patient hearing. We'll be continuing with the session 2 in few minutes. Welcome back, everyone. We'll be starting with the session 2 of the conference now. May I please request Dr. Swati Singh to become the session chair for this session. Everyone, we have with us Dr. Rajiv Kumar Srivastava, Director, NXT Semiconductors, Bangalore, who will deliver his address. Dr. Rajiv Kumar got his PhD in Electronics Engineering from ITBHU in 1995. He managed the activities in VLSI design complex SoCs with acceptance of all the challenges in the VLSI design market. His specialties include full chip design with special emphasis on RTL GDS implementation activity for mixed signals SoC and custom IP design with special emphasis on SRM, cache RAM, CAM, register files, and other modules for system on chip design. Dr. Rajiv, you can take it forward from here.
Okay, thank you. So I will try to share my screen first. I hope you can see my screen.
Yes, sir, it is visible.
Okay, very good. Okay, good afternoon to all presenters and participants. It is always nice to work with Professor Mehra. So thanks to Professor Mehra for inviting me for this very nice session where I am getting chance to interact with academic research, which is always, I mean, I always love the academic research. And the reason is very simple, that whatever academic research is done in different university, it basically sets the trend for the innovation for industries. I mean, you can see that whatever paper published 10 years before are now practically happening in industry. So basically, all the academic research opens the gateway to the development and product development happening in all the industries, not only VLSI, but it's true for all the industries. Now let's start with the innovation, because that's the key focus of this conference. So if you see, I mean, for VLSI, of course, transistor is the basic innovation, which is actually a basis of all the systems you see around yourself in the whole world. Now, if you remember, I mean, these are the basic transistors. Okay, whatever hardware you are making in VLSI, it's all transistors. All softwares running on these hardwares are possible because of these transistors. All the systems you are making, again, is possible because of only these transistors. And then, of course, a lot of applications are there. So all are basically driven by these two transistors, which is a great innovation of this, I mean, the century. In fact, last century. Now, let's move on to the journey of transistors. Now, I will go from a different path. So if you see, this was the first transistor invented by William Shockley long back. Now we have BJT, then we have FET, then we have MOSFET, then CMOS, and then, I mean, even I don't know whether you are aware, but in CMOS also we have different types of transistors. Of course, basic CMOS is for microcontrollers and digital analog, which you all see, and a lot of you must have using it or studying it in your colleges or practicing it in your research. Then we have FinFET, which is a new innovation. Of course, it started from Intel, but now it's also adopted by TSMC. So this is available for the any company who want to make, and this is available beyond 16 nanometer. So FinFET is basically a high-end processor used for high-end processor. All the recent microprocessors which are running at high speed and have a lot of compute power are using FinFET. Also, we have FDSOI, which is also used for high-end processor. FDSOI is different from FinFET, you all know. This has an advantage over the leakage current because of the insulator layer. And this was first initially developed by ST Micro. And then it was again, now this is also used by Samsung in their fab. So this is also very popular. Then we have a GO2 and GO3 MOSFET. So you know, I mean, we have a lot of electronics does not have only the applications in what we see at our home, like laptop, TVs, mobile phones, but also in industrial application. And there we need a very high voltage devices which are operating from 5 volt to 30 volts. So that is also done by GO2 and GO3 devices. So GO2 means gate oxide second and third. So the gate oxide one is the basic gate oxide of the CMOS, which all basically scale down with the channel length. So that is very thin. But GO2 and GO3 are thicker oxide. And there you can go for high voltage without any breakdown issue. Then also we have a SOI, the silicon on insulator transistors, which go at very high voltage from 60 volt to 100 volt. And that is mostly used for power electronics, and also a lot of it is earlier used in automobile when we were having the flash lamps as a headlight in the cars. But now, you know, everybody is switching to LED lights, so there the voltage requirement is quite less. Then, of course, we have BiCMOS also, where we need a high drive or high speed, but not a low power, high power consuming. We use BiCMOS. So, of course, yeah, I mean, everybody shows the channel length path, but I wanted to show this path also because this is also very key. And in NXP, we have all these things in use, and I will show you how. Now, let's go to the VLSI growth. Of course, this is the famous chart you all know. So we have, I have taken 1995. This is when I started my career in the industry. And when I joined ST Micro at that time, this was the channel length which we used for design. And now then it keep on going. And now today the situation is that we have up to 7 nanometer in production. So we have chips which have a channel length of 7 nanometer for transistors. And of course, 4 nanometer is in development. This is all industrial path. But if you see the academic research, you may go beyond that also. And that's how it works, that academics always show the path to industry where it can go. And of course, one of the limit we are reaching is the quantum computers. And in fact, the previous session, both the papers were very closely related to the field where in which the quantum computers belong. So just wanted to show you that we always see growth in terms of nanometer. That we assume that the company who is using lower nanometer is the best one, but that is not true actually. In NXP, we do production in 180, and in fact, most of the automotive and analog devices are made in this technology. We don't need this much costly technology to have a lot of devices. This is only required where we need a very high computing power in terms of speed, frequency of operation. Then we go for these channel length. And just to give you some examples, that all the high-end smartphones uses these channel lengths, and of course all the computers, including laptops, uses these channels. But if you go down, if you go to sensors, if you go to some microcontrollers which are used in automotive, they may be operating at lower channel length. The reason is very simple. At lower channel length, the cost of the production is very low as compared to the high end. So this is important to know that in industry, if you see our, especially in NXP, we hardly have 5 to 10% of device which are used using 10 nanometer. Rest all 80% are in the below 40, 28, or even in 180 nanometer. And this is important to know. And in fact, for students who are participating here, I just want to tell, don't assume that if you are working on this, then only you are great. No, that's not true. You can do a lot of innovations in these channel lengths also. Anyway, just to give a picture of the future. So this is what Intel roadmap is. You know, they are pioneer in reducing the channel length. And you see this 20 Armstrong. This is, they are showing the limits as for today. And just to tell you one very funny thing, that when I joined the industry in 1995, that time the technology was 5 micrometer. And people told me, especially my seniors in the industry, that in 10 years, VLSI will saturate and we all will lose our job. And even today, I hear the same, that after 10 years, VLSI will finish. So that 10 years is shifting, and I don't know till when it will shift. I think it will keep on going. And it will be never-ending job because of innovations. We keep on innovating different things which keeps all the VLSI people very busy. And again, thanks to academic research. Okay, now let's come to another thing which is very important to understand, which is the VLSI innovation cycle. And that's very key to understand. Now, we always talk of technology shrink in VLSI, but I want to go beyond that. In technology shrink, you all know that every shrink is basically by a factor of 0.7. So suppose you have 0.5 micron, you multiply by 0.7, 70%, so it becomes 0.35. And because why 0.7? Because if X and Y has 0.7 reduction, so it gives you an area reduction of 0.49, which is 50%. So the thumb rule is that with every technology shrink, you reduce the same chip area by 50%. Although it's not true, it will be slightly more, but ideal situation is this. So with each channel length shrink jump, you get more, either you get a smaller chip, which is cheaper in terms of silicon cost, or you have a flexibility to add more transistors, means more functionality to the same area of the silicon with respect to the previous technology chip. Then the second thing which also runs in parallel is the memories. There are a lot of development on memory side. We have SRAM, DRAM, ROM, EEPROM, OTP, and flash. Flash development is something which has changed the whole world, especially in the storage field. Now, in the latest equipments, we have flash memories which act as a hard disk also. So apart from this also happens in parallel. So basically, you get twofold updates with the technology shrink. The third one is continuous evolution of new architecture of each technology shrink. The moment they get you move to new technology shrink, these engineers say, okay, now we can add more functionality into the same chip. Let's do that. And in that way, they put a lot of things into single chip. And you can see a lot of examples, a lot of architecture development. You have cross-site CISC processors, RISC processor. VLIW is very large instruction word where you have parallel processing. Snapdragon is the Qualcomm processor, which is used in most of the smartphones. And then, of course, we have general purpose microcontrollers, which are very specific to certain applications. So those are cheaper because people always put limited functionality, which is focused for the purpose of the microcontroller. So the chip area reduces. And the last one is automotive microcontroller. And, a lot of automotive development has happened recently because of VLSI. And today's, I will try to focus on that also because NXP is one of the pioneers in that. And the fourth one is more complex application software. So you see, this is a continuous cycle. We have a channel shrink. We can add more memories. We can add more new architectures for the processor. And that enables more complex software development. And it keep on going. And that is why you see it's not a one-fold, but four-fold speed by which this innovation is happening. And that is, of course, it's a big team which is involved here. A lot of people working together and parallel and just basically complementing each other. Okay, now let's move to the systems. So what systems we have now because of this innovation cycle, which I showed in the previous slide. So of course, automotive. I will just spend a lot of time on this now beyond this slide. Then also we have smartphones, we have IoT, we have high-end computation, which includes quantum computer also. So by the way, quantum computer will be a reality. It will not be a situation like we have superconductors. It's going to be a reality, I can guarantee you. Then we have a lot of security. It's not home security, it's a lot more than that. It's not our computer security, but it's beyond that. I can give you some examples that even car requires a lot of security so that nobody can steal it. Even a lot of securities are there in your phone, in your laptop for the data. So data security is there. And now the most important thing, which is also coming in the healthcare, is the security of healthcare system. I can give you a very simple example. We have one product. It's a collaboration between different companies. I cannot take the name, but one company is making insulation pump with insulation sensor. So the whole system is like that. We have a sensor which detects the blood level in your body, the sugar level in your blood, sorry. And then it will calculate how much insulin is required. It will pump it automatically into your body. Now, it also has a feature that you can read the data, how your blood sugar pattern is following. You can read that data through NFC, which is called near field communication. It's a feature of a mobile phone. You can just bring the mobile phone close to that sensor and it will read. Now, the moment you create an interface with the external world, there is a high chance that somebody can hack it and they can pump insulin more than the quantity which is required. And that's a life and death situation in terms of security. So there also we have to, the half of the cost is on product and half of the cost is on security, so that nobody can hack it and system works with the full security without any issue. So this is very important. And healthcare advancement, you all know, so many equipments have come around, so many monitoring systems have come around. You can have, in fact, virtually a ICU-like system in your home also, where you can monitor everything. And of course, in healthcare, the most advancement is you can see through apps, you can talk to doctor through video call, and you can show where is the problem, and they can give you a medical advice also. They can also have a look to the your reports all through online, sitting at home. And also now the next thing in healthcare is basically senior doctors sitting at some other place and guiding junior doctors to do an operation remotely, and that's possible. And then, of course, the space science and satellite-based communication. I don't have to speak. You all know. India, especially India, is very far in this field, and this is all. Again, I'm coming back to my point. This is all possible because of lot of research done in the by the academics, by different universities 10, 12 years before. They thought of those. They have so much vision of things which you are making now at that time. And they did research in small pockets, and industry clubbed all them and make those systems. Now let's move to the automotive part, and I just want to show how far we have put the whole VLSI into our car. If you remember, when I was child, that time we were having only Fiat and Ambassador car, and they were having zero electronics. It was all electrical and mechanical, and of course, electrical and mechanical only. Now, if you see a high-end cars, they have up to $600 of electronics into one car. So you can assume how much it has gone up. Now let's see how we have penetrated into the automotive for safe and secure mobility. So we have a lot of things which are part of the car. So ADAS and highly automated driving. So ADAS means automatic driving assistance system. Infotainment and in-vehicle experience, automotive connectivity, body and comfort, powertrain and vehicle dynamics, vehicle networking, and functional safety and automotive security. Now let's look at all one by one. So first of all is the ADAS. Now this is very important, and this is all possible because of radar system. Now the good part is that with CMOS we can do RF designs. And we have inductors fabricated into the chip, which can act as an antenna for radars, both for sensing and so we have both receiver and transmitter. Now you can see if car has a small different types of radar, they can do a lot of sensing. They can control your speed. So cruise control, you all know in new cars, you have a cruise control where you can fix the speed of the car if the road is vacant. That's more used in US and Europe, not in India, because India you cannot get a full stretch which is very clean for a constant speed, but it's still a good feature. Now adaptive cruise control means you change the speed automatically just by sensing through radar what is how the traffic is, and this is might be very useful for India. Then we have autonomous emergency brake. So here, autonomous means you don't have to apply the brakes. The moment car will sense that something is behind, ahead of that, which is in the danger range, it will automatically press the brake. Then blind spot detection. You know, there is a blind spot whenever you drive the car. If you see on the back side, right and left, slightly diagonally, left and right, those things are not visible even in the mirrors also. You can see the back side, you can see the front, this side, but not this side. Those are called blind spot. Now through radar, you can detect those spots also. And if there is any obstacle there, you will be warned either, or maybe if it's a high-end car, it will take automatically the action for that. Then front rear cross traffic functions. So that is used for several reasons. That is mostly for crossings where you have a red light, green light, whatever. And apart from that, also if there is there is no traffic light, then it will sense if the traffics are going on or not. And based on that, they will take a decision. Then lane change assistant, parking assistant, and of course, you have a 360-degree perception while sitting in the car. So this is all based on radar. Then we have a vision where you have a video camera, like a webcam or whatever. Now, you know, vision, of course, gives a good picture. You can see on your screen or that what is behind you, what is in front of you. But unfortunately, video camera cannot tell you the distance, how far the object is. That can be detected by only radar. So that's why in automotive, radar is the main thing which is in use. Vision is mostly used for pattern recognition. Like if somebody is searching for a petrol pump, they can look into the video and see if there is any board which is board of petrol pump. So they can tell you. And of course, safe central compute. This is also very important. So this safe central compute means you have all the data from different sensors of the car coming to a central place, and then it's computing on real time to take a decision for movement or braking or parking or whatever. Now you can see this is the different range of radar in this slide. So you can see for the front, they have a higher range of radar. Then for different traffic and emergency braking and lane changing, you have a little bit smaller range, but with wider solid angle. And then, of course, cross traffic alert, which is the car nearby you and other vehicles. So for that, again, so basically you can see different radars with different range and their coverage, or what you call the angle. How much they can cover in 3 dimension. So you can see a car can have several types of radar, transmitter and receiver. Both is required because transmitter receiver together detects how far the object is. And of course, with different distance. So you can see how much electronics goes into that. And of course, this all require a lot of data processing also. So the whole system works like that. You have a sensor. It's a radar, vision, or V2X. I will come to that. What does it mean? And then you just take the sensor data, digitize it, and send it to the main area, the main processing unit. And then, of course, you have a secure network, which ensures that nobody is able to hack the car system. And then you have a lot of actions which need to be done through actuators. So basically, you sense it, do the processing, and apply the actions based on the data. And of course, you have a digital networking infrastructure, which means that you are also connected to the big data, which is centrally governed. Either it's related to traffic or road or a way to go, or the simple example is Google Map. Okay, then moving to the next one is the entertainment and connected radio. So of course, entertainment, you all know there are a lot of amplifiers and music systems, all those things are there. In radio also, we have a lot of, AM, FM, we are all familiar with, but now we have digital radio also, we call it DRM. And this digital radio works on AM. So the advantage of this is that this digital radio has a quality of FM in terms of sound quality, because in FM radio, you don't see any noise because it's a frequency modulated, so there is no noise. But the range of FM is very less. It's limited to cities, or it's a point-to-point contact communication. So you cannot send it using your ionosphere as AM. But digital radio has a digital transmission, so the noise problem is solved. So the quality of sound is like FM, while the transmission distance is like AM. So even you can hear the radio channels of different other cities close by, or even beyond that, through digital radio. And by the way, Prasar Bharati is also working on it, and they are making standards of it. So most likely in future we will have digital radios also available. Although it is available in the cars, but transmission is very less. But good news is that the transmission of digital radio has already started in India. So this will be coming very soon. Okay, and these two, and then USB Bluetooth connectivity is also important. You might have seen that now in cars you can connect your mobile phone with the system audio and system, and you can hear music, or even you can talk while driving without using your phone on your ear. Although it's not recommended, it's by law, it's not correct, but it's possible, at least for others who are not driving. Then the next part is V2X communication. Now this is also very important. Now vehicle to everything, V2X communication is called vehicle to everything. Now vehicle to everything means that when you are driving and there is a crossing, of course here it is shown as a flyover, but you can communicate, you can know that, okay, any car is coming from this direction, that direction, and they can talk to each other. Suppose they are not visibly visible to each other, and they might not be in the range of the radar, but still they can talk, and they can tell that, okay, if both are crossing, going to cross like this in a crossing, they can tell each other, okay, let's slow down, otherwise we will collide. So this is something which is now practically possible. Earlier it was done through a Wi-Fi system, which was supposed to be laid down in all the highways, but now with the coming of 5G, this may be a reality very soon. So as I said, by making invisible visible, that's the most important part of the V2X communication. And this is also now part of a lot of cars. Okay, the next one is, by the way, this V2X can be also used for like Ola and Uber systems also, because you have a connectivity from V2X. In fact, this is practically happening also now. Then you have a smart car access. So smart car access, earlier I remember I used to hear a lot of thefts of car happening when I was child, or even when I was a student, because you can make a duplicate key and you can switch on the car and run away. Now with the RFID solution, this has gone. You can lift a car, load on a truck, then only you can install it. Otherwise, you cannot switch it on unless until you have the correct RFID key. Even when you buy a new car, you get keys, and if you lost it, then you have to go back to the vendor, company, and ask for the next key, and then they will make a next key. So this is very good. And now earlier this smart car access was used only for high-end car, but now it has been used even in motorcycles. For an XP, Mahindra and Suzuki and even Honda are our big customers, and even in motorcycle they use such keys. Now the next generation in this is that we are making NFC, using the NFC connectivity to make our mobile phone as the key of the car, and that will happen very soon. Okay, then next one is body and comfort. So the most important thing is airbag and crash detection. So this is one of the key things. You must have seen a lot of advertisement showing that this car has so many airbags. And so the good part is that whenever there is a crash, the airbags will open and it will protect you. And that's one of the very important things. And we spend a lot of, not only we, every automotive company spend a lot of money on this, because this is one of the key features, and everybody would like to have it. Then you have a lot of things on the lighting part. Then you have electric pumps. This is mostly for the pumping the fuel like petrol and diesel. Tire pressure monitoring. So now in these, you can see that you can have a pressure of your car tires available on your dashboard, heating, ventilation, and air conditioning. Then next one is powertrain. So this is important for electric vehicles, and now the electric vehicle is become reality, and Of course, India is also working very hard to build the whole infrastructure for charging stations, and soon it will be reality, I know. So that way, I think in few years from now, most of the people will be driving electric vehicle, especially inside the city, maybe not outside the city. So there are a lot of electronics involved in the electric vehicle. The reason is that even for charging the lithium-ion battery, you need a lot of electronics, which is called battery management system, because the charging and discharging of lithium-ion battery is very sensitive. So you have to take extra care of that. Then, of course, we have a lot of things on the engine side, and then, of course, on the vehicle dynamics. Okay, I think this one is my last slide. Then we have vehicle network processing. So this networking is inside the car. So you have a lot of sensors, a lot of systems, a lot of things, and you have to connect each to everyone so that you can process the data at a central place. And also this gives you connectivity from outside also through V2X. So you have so basically with the help of V2X and VNP, you can control all the parts of car remotely. Vehicle to grid is something which just guide you if you want to charge your station, and if suppose your battery is going down, discharging soon, so automatically it will alarm you, and also it will show you the location where the charging station, nearest charging station is there, and it will ask you to divert towards that. So this is also a very important feature, and it will be a future, it will be heavily used. Okay, the last slide is on functional safety. So this is something which is a very important feature in the automotive, and VLSI has to play a lot of roles here. So functional safety is basically a system that depends on automatic protection from any possible failure. So basically, for functional safety, for any functional implementation in the chip, there is a functional safety team which ensures that if this failure happen, how our chip will react to ensure that everybody is safe. And first try will be to avoid that, if not possible to avoid, to ensure that car and the people who are sitting inside the car are safe. This is very niche field. A lot of people are working on this, and it requires a lot of innovation is still going on. Of course, it is controlled by ISO 26262 because this is related to safety of people. So that's why there is a very strict standard through which it is followed. And of course, automotive security is always there just to ensure that nobody hacks the car from outside, which is very dangerous. Okay, I think this was my last slide. Thank you for listening, and over to you, Vaishali.
Thank you so much, sir. Please accept our token of appreciation from the team CIR.
Thank you very much, Dr. Ajib, for such an elaborative details of innovations in VLSI technology.
Thank you, sir.
Now, I request Professor Dr. Ashok Dey, Emeritus Professor, Delhi Technological University, Delhi, to deliver his talk of concept. Dr. Ashok Dey got his PhD in microstrip antenna from Indian Institute of Technology, Kharagpur, and his master's and bachelor's degree in engineering from Javadpur University with honors. He has served as a director of National Institute of Technology, Patna. He's an experienced director with a demonstrated history of working in a higher education industry. He's a well-skilled in e-learning, strategy planning, lecturing, organizational development, and educational technology. So,
oh, thank you, Vaishali, for your introduction. And firstly, I want to thank the organizer, especially Professor R.M. Mehra, for giving me the invitation.
Namaskar.
Namaskar. Namaskar. After a long time, I'm seeing you.
Yes.
So, without any delay, I can start my presentation. This is. Can you see? Hello?
No, not
No,
yet.
sir. No, sir.
Not yet. Okay. Why it is not coming? Yeah. Okay. Still it is not coming, no?
No, sir.
Okay. Just 1 second. Just 1 second. It is like this.
Sir, there is a button which is square having the up arrow key. Kindly click there.
Can you see now?
No.
I can see. Can you
Yes.
see now?
No. Yes, we can
Okay,
see now.
okay, fine.
Yes.
Okay. So in this half an hour talk,
Please make it full screen F5. You can.
I'm doing. Just 1 second.
F5
Mhm.
full screen.
I know. Just 1 second. Please hold on.